Hello, I'm Bernie. I'm from NewT.exe FGC 21780, and I'm the team captain hardware lead.
I'm Solomon. I'm from the same team, software lead, I guess.
All right. So at the beginning of the season, there were a couple of goals that we wanted our robot to have. First, we wanted it to be able to be small and as small as possible and maneuverable, so we can move around all the junctions. Second, we wanted to minimize drivetrain movement, as we saw that in previous games. Drivetrain movement was generally the slowest part of the game. And finally, we want a low center of gravity. Since we'd be sending a lift really high, we wanted to not tip. So starting off with a robot, we have our drivetrain, which is a 14-inch by 16-inch Mecanum drivetrain, so a bit smaller than the size limit, which lets us easier get around the field. Using Mecanum wheels, which allows it to move in any direction, meaning that we don't have to turn before moving sideways. And finally, it has a set of 3 Adamji pods, allowing us to accurately localize ourselves during the game. For intake, we went for an extendo intake. Our intake is not on parasite that can extend 4 feet, and this lets us minimize direction movement and occasionally even, for example, on the close high junction, even cycle in place. Went for claw because what that lets us do is it lets us sort of like run into the cone and grab it instead of having to position ourselves directly over it, saving time on alignment. And the cool thing about our claw actually is that it can over center, meaning that once it's closed, it's really hard for something to pull it open unless the robot wants it to. And finally, our intake arm is counter sprung, meaning that we have elastic tubing in this case, pulling it back towards the vertical position, and this helps offset load on the servo. After our intake grabs it, it transfers it over to our outtake. which is a passive outtaking mechanism mounted on a set of hybrid double reverse 4-bars. Now, these double reverse 4-bars have a virtual 4-bar section on the top and a full 4-bar section on the bottom. And since the virtual 4-bar section uses plastic chain and only one linkage, it's light, allowing us to save on weight, while the full 4-bar on the bottom is heavier and sturdier. And what that lets us do is it lets us have a good balance of stability and weight, as well as lower. Since we put the heavier section on the bottom, it allows us to lower our center of gravity. And for our actual outtaking mechanism, we went for a passive outtake where the cone or the junction itself takes the cone off the pole. And that way we were able to put depositing and attraction into one motion, saving time, and lets us use the cone itself to align with the junction.
So in autonomous, one of our biggest challenges was cycling 5+1 cones onto a line side junction, because we have to simultaneously move a drive in a spline, move the intake, and move the outtake. And to coordinate this, we use Roadrunner with multiple trajectory sequences and a custom fork of FTSIB's command system, which I'll explain later. And some of our all modes have the ability to abort when we detect that a cone is missing or we're running out of time, to make sure we have time to park and avoid penalties. So our output inheritance structure allows us to avoid duplicate code, which means that if we change code in one place, it'll change everything we need, rather than having to remember to change a bunch of separate places and keep them in sync. So in our code, we have new auto implementing the overall structure. Then we have a separate auto for each position for the junction, which define the trajectories. We have different intake-outtake sequences, depending on how many cones you want to try to deposit if something goes wrong. And we have left and right, which just for the two sides. And so FTC is a command system. So we made various changes. So first of all, the command system lets us coordinate commands like more advanced state machine, and we split up some features, merged other features. One key thing we did was change the callback system to better improve its support for logging, so it can output information about what's going on to a log file, so you can look at it later and figure what the robot's doing and to help with debugging. In our intake, so we have a sensor on the end, that a distance sensor that detects how far the cone is, and teleop, it automatically slows down as it gets close, and then auto, it when it gets close, it detects how far it is and calculates that's the target position accordingly. And then in both modes, when it gets very close, it stops and closes automatically. Vision, we use April tags because they're easy to detect, and we found an open source implementation. We use 3 of them so it can detect from all angles, and we use the closest match to avoid detecting your opponent's cone. Any questions?
Sure. So our robot this year, this is actually the first robot we made that's completely made out of metal. And for this, we actually built our own CNC machine. And over the past 3 seasons, we've been slowly testing on various materials. And this year, we're finally able to get a good profile for aluminum. And what this let us do is since we can machine the aluminum parts in-house, it let us iterate extremely quickly on our subsystems. For example, our lift didn't originally have this section in the middle. This section in the middle was actually added to add clearance for this servo on the top. But because we were able to machine aluminum in-house, we decided that we would add this section, even though it was fairly close to competition. And that helped improve the reliability of our robot.
We had a couple questions come in from chat, by the way. First one from Screen 404. What was the difficult part of using extending intake?
On the hardware side, definitely wiring. Because we also went with a double reverse 4-bar, that means that the side sections of a robot are basically all taken up. And we couldn't easily run a a wire loom or a huge like scissor lift wiring thing in the middle, because that's also where the arm went back. So we went through a ton of iterations of this wiring, and what we eventually ended up with is we attached it all to the underside of our slide inserts with a bit of elastic tubing in order to make sure that when it retracts, it sort of falls into the right place for it to not get tangled up.
I guess on the software side, the biggest thing is that the farther we extend the intake, the more precise we have to be about our robot's rotation in order to line up with the cone properly.
I'm going to combine these two questions into one here from Seedling Sinton, asking what was the most difficult challenge you faced this past season? And then Civ adds on, is there anything you would have done differently had you had the chance?
Sure. I'd say probably our most difficult challenge on the entire team was probably getting the 1+5 alliance high to work, which was a challenge both on hardware and software. Mainly because as the season went on, our Masumi slide slowly started getting more and more loose, and it started drooping, which meant that we needed to make some additions to our robot. So we added this set of idler wheels at the front in order to prevent drooping. And also, if I were to do something differently, I'd probably include some sort of turret mechanism in the outtake. Right now, it only deposits out the back, and that means that we have to constantly turn when trying to cycle on the alliance high junction. We actually did make CAD for a turret mechanism, but we didn't end up getting enough time to implement it.
In the software side, I guess one thing that would have been good to implement earlier is using the same control flow structure throughout, because our code is currently uses different ones in different places, and it's hard to get we have multiple software team members, so it's hard to get everyone to agree to change, especially once we have working code. We don't want to change it unnecessarily and potentially break anything. So if we agree decide on the start, that could help.
All right, chat, we'll give it just another minute if you got any more questions come in. Otherwise, NewT.exe, anything else you'd like to wrap up with on your presentation?
I guess in terms of difficulties, one thing I want to mention is that transferring took us a while to debug, as it always does.
Yeah, transferring was a mess. It worked perfectly well in CAD, but in the real world, there are some issues. For example, one big issue was there was some backlash in our claw mechanism, and what would happen is, so what our robot does is it lifts the arm and brings the slide back and pivots the claw all at the same time, and that means that the cone has to move very fast, and this backlash would mean that it wouldn't move precisely where we wanted it to go, and it would sometimes miss the transfer. We eventually iterated on these claws on our outtake, and what we were able to have them do is have them automatically funnel incorrect transfers into the correct position, or inaccurate transfers into the correct position to deposit, which helped solve the issue.
All right, well, Newt, thank you so much for appearing on there. And chat, thanks for your questions as well, too. We're going to be heading over and getting ready in just about 6-7 minutes for our next team, which is 8393, the giant Diencephalic BrainSTEM Robotics team. Thanks a lot, Newt.
Thank you.
Thank you.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in FIRST scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first.
Hi everyone, I'm Lucas, and this is Mahir, and we're from Team 8393, the giant Diencephalic BrainSTEM Robotics team. So I'm one of the lead designers, and Mahir is a programmer on our team, and we're sort of going to go through the robot and explain how we balance between design optimizations and program optimizations to account for whatever is on our robot. So to begin with, I'm just going to do a brief overview of what our robot does in a big picture. So first, going with the drivetrain, this year we utilized the Rev mechanical wheels, so about 3 inches, and they're powered by a beveled 16-to-1 motor. We also utilized 3 linearly sprung odometry modules, 2 parallel, 1 perpendicular, for accounting for position on the field during auto. Then, sort of just moving into our scoring mechanisms, we start with our collector. So our collector is just a standard claw. We utilize two 3D printed parts with rubber bands in the center to account for the curvature of the cone to maintain that robust grip. We then have a 4-motor lift that's able to launch the cone to its final destination very quickly. We also have a mini servo turret up top. It's able to go to any direction, and an extension. So we can basically just deposit from wherever we are in the field, whether that be in teleop or in auto, for the perfect placement of the cones. So the first thing that I want to talk about is sort of something that we do every season and that we think is essential to have success, and that is a design iterative process. So for us, this means that at the beginning of the season, we design multiple approaches to every subsystem in CAD right away. So we'll have multiple people designing their different ideas, or maybe we'll just have smaller different fixes for each subsystem. And so once those are all designed, we're able to easily manufacture them quickly and inexpensively out of materials like wood, so that we can build it quickly, we can test, and we can evaluate whether or not this is minimizing our scoring cycle time, which is the sort of target metric for if we want to use a subsystem or not. Once those designs prove themselves, we can then transition into more robust materials, such as FR4 or epoxy glass laminate, which is all the black material that you see on the robot. Or this year, we also use some aluminum. So we use aluminum on our lift slides and the base plate for our turret. And so we use this just for a more robust connection, and we're able to thread it so that reduces more space as well. And so when it comes to the iterative process, there's also another step that really adds ease of use, and that's balance between simplicity and modularity. And so when I say modularity, I just mean the ability for you to remove a component out of the robot really easily, so it's able to be fixed if it gets broken, or if you have a new design that you want to test out really quickly. It's not optimal to have to redesign the entire robot for just one subsystem. So if we look at the pictures that I'll be sharing, we start out with just the base of our robot. So this is sort of the empty shell, if you will. So this is the drivetrain and the odometry by itself. And as you can see, we have a base plate and we have 2 walls that have mounting holes. And so this sort of lends us into the first step of the modularity, which is the lift. So the lift, hopefully you can tell on the sides, has tabs, and it uses Rev nut strips. So we're able to slide it into the side panels and attach it with 4 screws on each side. And then we also have a maker beam frame that surrounds our 4 motors, which allows us to use 4 screws from the bottom to attach it. So we have 3 sides of attaching, but it only uses 12 screws. So we're able to easily remove it if something happens, such as if the string snaps, we need to replace that, or if we need to replace a slide. The next subsystem that uses modularity is our rotation system and just central structure. So this system just needs 8 screws to be removed, 4 from each side of the lift, and then the entire system can be removed. Within the system itself, the turret can also be removed with only 4 screws, and the extension can as well. And then finally, we have the collector, which also can be removed with simply 4 screws going into some Go Build quad block mounts. So, and the really nice thing about this is that we're able to swap out for alternative designs, such as this old collector that we had. We can easily replace it with the existing extension without having to make any modifications whatsoever. And so now that I've talked about simplicity, modularity, and iterations, I'm going to sort of focus on one subsystem in particular that really, added the biggest advantage for our robot this year, and that's our 4-motor lift. So this year we had 4 5-to-1 motors that are all geared together for our lift, and so then we had 2 extension pulleys to power the 2 sides and 1 retention pulley in the center to pull it down. And so this allows us to launch the cone to the high junction in under 0.7 seconds, and really just gain that speed advantage. And so I'll hand it over to Mihir now to begin talking about the optimizations that went into that.
Yeah, so the main goal of our software this year was to maximize the potential of our subsystems while also accounting for the nuances of our robot. Looking at the lift in particular, you can see that it's a very complex mechanism that has a lot of nuances. For example, when the lift goes up, it requires more force the further it goes up. So what we used to account for this was a PID controller where the proportional part would smoothen out the movement of the lift, and the derivative part would account for the change of error over time, where if the change in error slowed down, an additional power would be applied so that the lift would maintain good speed at higher heights. And then the integral part, which would allow the lift to get to the desired position and add more power if it wasn't getting to the desired position over time. Another part of our program that we try to optimize in particular is time. So we use video analysis throughout the season to look at our autonomous and see where our robot is pausing, where different actions can be parallelized, or other optimizations. So Lucas can show a video of our early autonomous in the season. So you can see here that the robot is quite, it has a lot of pauses in its movements. And throughout the season, we optimized it and found ways to maximize the mechanics of the robot, which you'll see in our MTI submission, where we got a 1+5 autonomous high pull, where we took many videos throughout the season, looked at where we could lower time. And one specific example was whenever we were initially trying to do our 1+5 autonomous, we had the robot move all the way to the wall and then try to pick up cones. But we found that we could actually optimize this by maximizing the potential of our mechanics and extending our extension before we reached the end of the wall to grab the cone instead, which we found was much faster and saved a ton of time in our autonomous. And yeah.
So that was an overview of our robot and the programming and the optimizations that sort of mix those two together, and sort of just the things that we learned and what we find is really critical for every year, regardless of what the challenge is. So we'll open it up to questions now.
Yeah, our first question coming in from Screen 404. Did the strategy change throughout the season, and how did it affect changes on the robot's hardware and software?
Yeah, for sure. So at the beginning of the season, one, I think, critical component of strategy, which I think many teams saw, was the circuit itself. And so at the beginning of the season, we found that we wanted to go for the circuit in every match, no matter really how competitive it would be. So our robot was immediately designed to be able to move around the field very, very quickly and deposit on any pole, regardless of its location. Now, the strategy as the season moved on sort of turned to just, covering opponents' cones, because as the matches became more competitive, circuits became less viable, and just doing it sort of wasted the points on the field. So in terms of changes to the design and to the software, we didn't make a ton of changes because we found that the mobility is still critical and the flexibility of depositing on any side and distance is still critical. It's just a matter of where we're actually placing those cones now.
And we also wanted to find ways to improve upon our robot, especially in our autonomous, where we, at some point in the season, we kind of saw that we were reaching our maximum potential using the mechanics of our robot. So we wanted to achieve better results. And the way we found we could do this is by adding this pole aligner, which was actually a very late change in the season that allowed our autonomous to be much more consistent. So just finding new ways to optimize the mechanics to better suit your strategy is what we focused on too.
I think one thing I didn't mention as well with the robot is that we have these cone flippers that we added pretty late in the season. But we found, as matches became more competitive, as I mentioned earlier, it became critical to have every single cone deposited exactly where you need it to be. And if you drop the cone, that could often, be the cause of your loss. So we add these cone flippers because in many of our matches, like there were fallen cones, whether it be a result of us or our alliance partner. And the ability to correct those mistakes and place it somewhere was really critical for us.
We got a couple more questions coming in. Quinn McGinley, I'm going to expand on your question here. They asked, how can you afford to keep all your robots like that in the background? Because you got a very impressive background. But I think more importantly, can you maybe just talk a little about how your team does fund development and how do you maintain your finances and fundraising, that sort of thing?
Yeah, so I think just largely we have over time we've accumulated resources. So we have our own laser cutter in-house that we've had for probably over 10 years now. We have a CNC router. So we have machinery, and we also have parts that we've accumulated over the years, whether it come from sponsorships directly from companies or money that we've received that we use to purchase these parts. So most of the parts that, especially on this year's robot, we actually didn't need to purchase new, we've actually had in stock, like within our shop. But in terms of how we fundraise, it sort of comes in different parts. A lot of it does come from sponsorships and just reaching out to companies in our area. So we present at conventions. So we do lots of outreach with these companies, have calls, and they're all very interested. Like it's really easy to get, especially engineering companies, to be like thrilled about the work that first teams are doing because they wish that they had the opportunity whenever they were younger to do it as well. So using those connections. And then also just at our outreach events, we have fundraisers, whether it be just like small things like concession stands or 50-50 raffles, all together throughout the season, it adds together and we're able to do stuff like this.
All right, we're going to have to go a little speed around. We got a couple more questions coming in here. One from C-League asking, given the modular hardware subsystems, do you time yourselves to see how quickly you could swap in a replacement module?
I think so. I'm not going to say for 100% certainty that this is true, but throughout the season, we had to remove the lift many times as we were iterating upon it. And I think over Thanksgiving break, we were having, some time crunches before our first qualifier. And I think we got it down to like 15 minutes to remove the entire lift, restring both spools of the entire lift, and put it back in completely so we're able to program it again. So, yeah.
All right, last question we're going to take here from Terry Faber. Besides the awesome robot drivers, what would you say is the primary reason BrainSTEM has been the Pennsylvania State Winning Alliance for the past 5 years?
So I think it comes, as you said, with the drivers. That's obviously one really critical role. Our past driver who just graduated this year, Nathan, shout out to Nathan, was the driver and he won for the past 5 years. So that's critical, just the experience that comes from that. But also, again, like with the iterative process, making refinements to the robot that can be easily tested and really quickly, fixed on the robot that allows us to have maybe a V2 or a V3 by states even. And so that sort of step up and, change in our robot is really critical.
Awesome. 8393, thank you so much for telling us more about your robot. And if you are watching live, by the way, we're going to have 19458 Equilibrium.exe coming up in just a little bit. But 8393, good luck into the center stage season. Thanks a lot.
Thank you.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in first scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first.
Hi, we are Team 19458 Equilibrium.exe, a community-based team from Potomac, Maryland. This past season, we were a division finalist at the World Championship, and FunFTC ranked us in the top 25. My name is Miriam. This is my 9th year of FIRST and 5th year of FTC, and I am the software lead on the team.
My name is Alex. This is my 5th year on the team. I'm a main engineer. I was co-captain of the team, and I was driver 2 as well.
This season, we identified two major strategies, a roamer and a stacker. A roamer would spread cones around to different junctions trying to gain ownership points, and a stacker would stack a bunch of cones on a single high junction. We decided that we could get under 5-second cycles either way, and decided to go for a roamer strategy to maximize our points with our limited number of cones.
In order to facilitate this roamer strategy, we decided that we wanted to be able to drop cones on junctions on both sides of a row. And so we did this by having a servo that can rotate our arm plus or minus 90 degrees. We decided that this would be a more elegant solution compared to a turret, since a turret has all the additional mechanical complexities, and we didn't need the full 360 degrees of movement. Additionally, one of our past members has had previous experience with turrets and gave us the benefits and drawbacks of each, and therefore suggested this. On the end of this servo, we have a horizontal extension, which replaced our old static mount. Our old static mount required us to have to shift the robot 1 or 2 inches in order to drop on the junctions on either side of a row, while this allows us to extend out our claw in order to drop, while still retracting in order to fit within 18 by 18. It's powered by the servo and a linkage and allows us this much movement. Our claw is an inverse claw. We like to call it a nose picker because it grabs from the inside of a cone right here. And we decided that it would be more advantageous than a traditional claw, since in a traditional claw, let's say you grab in the middle, you'd always have to grab there, because if you grab from the top, you run the risk of not closing the claw far enough or to grab, or if you grab at the bottom, you could run the risk of overdriving and then breaking a servo. And so we decided to grab from this top, which has a consistent small diameter. Additionally, we have this shroud on the outside of the claw, which also holds our beacon holder. It's 2 latches, which are held closed by surgical tubing, and then these 2 kind of Bowden tubes, kind of like the brake system on your bike, and then the spool, which opens and closes it, as you can see here. And so one advantage of this is that we can grab both at the same time, and then drop each one individually. And so how our claw works is that we have this servo right here, and it powers this linkage, which pushes up and down this plunger, opening these 3 claws. Now, one drawback of the fact that we always have to grab from this top area is that we have to be very precise with how we're picking up the robot, or picking up the cone with our robot. And so we have this cone aligner that allows us to pick up from a pretty wide area, but still feed into the same area to pick up with our claw. And what's unique about this cone aligner is that it can fold up with this virtual 4-bar right here, and it's kind of like your elbow and shoulder. Additionally, we found issues that if we were to hit the wall with this all the way down, it could break a servo, and so we added in a bar right here in order to help prevent that.
The entire process of picking up a cone is completely automated, starting with the color sensor in our nose picker, which allows us to detect when our drivers have reached a cone. Once that happens, our lift lowers until the limit switches in our nose picker detect a cone, at which point the nose picker will expand to grab the cone, and the lift will raise to prevent dragging the cone along the ground or knocking over a cone stack.
Speaking about our lift Our lift is unique in the fact that it uses 3 different sets of slides. It uses 2 sets of Mitsumi 3 stages, both of which are a different length, as well as 1 set of MGN carriage slides, which means that we can utilize the full length of a slide so that we don't have this extra foot sticking out, as you can see. Our slides allow us within these middle 2 rows to hit basically any junction and drop a cone on it within 5 seconds, and it lifts high enough that we have roughly 3¼ foot of space over, since we grab from the top of a cone in order to drop on a junction. Additionally, we have these 2 tape measures right here, since we found that sometimes when picking up a cone stack, it would get caught between 1 or 2 cones and lift the rest of the cones into this void here, getting stuck in our robot and causing issues. Additionally, 2 unique things about our robot is that we have aluminum odometry pod mounts which we replaced the 3D printed ones with, since we found that it had a little bit too much wiggle and would add in inaccuracies to our odometry, and that we use 75mm rev mecanum wheels over the traditional 96mm go build a mecanum wheels that everyone else uses in order to widen our wheelbase.
Our auto has fail-safes, allowing us to always reach the cone stack, and when we don't reach the cone stack, we will always get our 20 points from parking. In addition, our development process went quickly because we were able to use our symmetrical robot to mostly do our testing in one quadrant of the field and then easily translate our auto over to the other restarting positions. Thank you, and we will now be taking questions.
Cool. We got a couple questions coming in from chat. Screen 404 asking, did you improve on the design of your robot from the first qualifier through Worlds? And if so, how did you choose what to improve?
So we did make a couple improvements. One of the biggest ones was replacing our old static mount with our horizontal extension. So our old static one, like I said, we had to shift 1 or 2 inches horizontally to each side in order to drop on a junction, while our horizontal one allowed us to drop at a preset distance, meaning we didn't have to shift horizontally. And the issue we couldn't make our static mount longer was that it wouldn't fit with an 18x18, but with the slides like this, we can simply retract them in order to fit.
Next question coming in from Civ asking, can you elaborate a little bit more on some of your robot materials? I know you touched on a couple of them, but can you give us a little bit more of a general overview of some of the other materials you use on your robot?
So generally, we had our robot is mainly either custom cut aluminum that we cut by hand or got machined by a third party, or custom 3D printed. As you can see, this entire shroud and all of these blue accents are 3D printed. And actually, this right here is a aluminum side plate that we cut and sanded machined by hand. We then wrapped with a carbon fiber kind of vinyl wrap to look like carbon fiber. So it's not actually carbon fiber, but it looks like that.
Fair enough on there. I'm sure this is an inside question, but I'll ask it anyways. Drew Diedrich asking, hi, Alex, why is your shirt blue?
It's blue because I'm wearing the Equilibrium shirt, and blue is our team color that we decided.
All right, fair enough. Next question coming in from John Cannon. Did you find having a unique odometry setup gave you an edge over other teams during Autonomous?
So the reason why we decided to go for our aluminum odometry pods is because originally we had our mounts were 3D printed, and then actually at one point we decided to retune our Roadrunner, and we noticed on the localization test that we were consistently getting drift. And then when we looked at our odometry pods to see if it was a mechanical problem, we noticed that they were actually had a really large amount of wiggle in them, and so they replaced those 3D printed mounts with aluminum mounts, and that allowed us to have a much more sturdier mount, and we had a lot less drift after that.
So as you can see on the bottom of our robot, these are our Rev 75mm Mecanum wheels. And if you can see here, just a tiny bit of the odometry pod is, the bottom part is aluminum. But otherwise we have our 3 odometry pods right here, and the backing plate is aluminum. But the most you can probably see of that aluminum is right there.
Question coming in from C-League Sintin. I'm going to elaborate a little bit more on this. Asking more about the different iterations you went through to get to your final designs. I'm going to ask on top of that, looking at your team had a very deep run at championships in the Ochoa division and, of course, attended MTI as well. What did you look at doing for modifications specifically for championships and MTI?
So one of the modifications that we did for MTI was the odometry pods. We replaced them with the aluminum. However, some of the modifications that we made for World specifically was this horizontal extension, and we also eventually reduced some of the sharper corners on the cone aligner that we have in order to also help reduce the fact that we might pick up a cone accidentally. So combined with these tape measures right here should have greatly reduced the fact that we picked up a cone or part of the cone stack and dumped it into this void, preventing our robot from continuing further.
All right, so we start to wrap up. By the way, chat, if you have any more questions, we can take those, and we'll give Equilibrium a couple more minutes. Wrap up and talk a little bit more about their bot. So Equilibrium, as you look into the center stage season, what are maybe some of would you say are the most important things that you took from this season in Power Play that you're going to apply to center stage?
So if we assume that odometry is going to be used during center stage, which is possible, but it's also possible that you could do camera localization with the addition of April tags, is that you want to make sure that your odometry pods are really sturdily mounted, because one, that reduces just some of the inaccuracy. And also another issue that we had with the 3D printed ones is that sometimes the bottom would snap off, and we'd have to replace that 3D printed mount.
And I'll follow up on that too. Miriam, is there anything from April tags that excites you of having that for the first time in FTC? Because last year in FRC, they introduced that. A lot of great implementations. What excites you most about April tags on Equilibrium?
So I really like the idea of April tags as localization, because we found, like, I actually did some initial testing on it earlier this summer, and it was like very good, like, because what we were doing this past season in auto, we would use ultrasonic sensors and IR sensors to make our small corrections for odometry drift, and it would be really nice to be able to use April tags instead, because that's only like 1 or 2 sensors that we actually need to add our camera, which we'll probably want anyway, and it will also, it's just more accurate and precise than the sensors that we were using this past in Power Play, from what I can tell so far.
All right, Equilibrium.exe, thank you so much for telling us more about your team, and hopefully everybody's finding great value. I think they will. So thank you so much for that. Good luck in the center stage season. And if you are watching live, up next, we're going to have 14496 Roboctopi coming on in just a little bit. Stay tuned. This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in FIRST scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first.
Hello, we're team number 14496 Roboctopi. I'm Nico, the team captain and the primary robot designer.
And I'm Sherwin. I'm the primary chassis driver and also programmer.
PowerPlay was our 5th season in FTC, and it was our first time going to Worlds. We actually saw huge success at Worlds this year. We were division champions for the Ocho division, with Wolfpack Machina and out-of-the-box robotics. And we also ended the season ranked 5th on FTC stats. So how did we get here? I'll cover some of the hardware innovations that made this possible. Our Freight Frenzy robot was functional in that it could complete all aspects of the game, but it was very complex with lots of different systems. This made it somewhat unreliable because there were many different mechanisms that could break. It was also very difficult to program for optimal performance because of the sheer number of mechanisms that we had to code. So this year we went for simplicity. Outside of the four chassis motors, we have 2 motors and 3 servos on the entire rest of the robot. This made it far easier to control because there's way fewer mechanisms that can fail, which also increased our reliability. However, we don't strive for simplicity at the cost of performance. We pack lots of functionality onto the few actuators that we have. So for example, our intake servo, which opens and closes our claw, has 3 different functions on it. Firstly, it can obviously pick up cones, but secondly, it can also pick up our beacon. So we pick up both the cone and the beacon at the same time, and then we can drop just the cone, switch to a different pole, and then drop the beacon by itself. This allows us to claim 2 different junctions and increases our ability to create circuits in endgame. And then the third function is it can also collect cones that have been knocked over. So we can drive up to them, flip them up, and then intake them like normal. So these 3 different features are packed onto one single actuator on the robot, which allows us to maintain that simplicity. Flexibility is also really important so that you can work well with any alliance partner no matter the randomized match. So this is why we created a small and light robot that can easily navigate anywhere on the field very quickly to any pole. The robot is also fully symmetrical, which allows it to intake both on the front and the back of the robot, as well as deliver on the front or the back of the robot. And this also works for both autonomous and teleop. So this greatly reduces the number of rotations that our autonomous has to do, and as well as our drivers, because we can switch just with a simple toggle button between the 2 states. It is often fastest to move the cone on the shortest path from the substation to the pole that you're trying to score on. And this is why we don't have a transfer on our robot. The intake and delivery system are fully integrated onto one mechanism on the robot. Additionally, we knew that the fastest way to deliver cones was to take advantage of every mechanism on the robot at the same time. So when delivering a cone, the chassis is driving to the pole, the lift takes the cone up to the pole's height, the arm flips the cone to the other side of the robot, and the wrist tilts the cone towards the pole so that we can score even faster. All of these different actions happen at the same time, and there's no mechanism dependencies. This makes our cycle times even faster. Finally, we optimized the weight distribution on our robot. We knew that center of gravity was going to be really important this year to maintain a stable robot because we had such a small footprint as well as a lift that could lift all the way up to the high goal. However, we didn't want to add a dead weight to the bottom of the robot because we knew that would negatively impact our agility on the playing field. So this is why we optimized the weight distribution of the robot, such that the 4 chassis motors are placed as low to the ground as possible, and then the lift motor and the battery are placed right on top of them. This is the majority of the robot's weight, and it's all very low to the ground. And because of this, we were extremely stable this year and never had any tipping issues, even though our robot was the lightest we've ever had it at only 28 pounds. We even optimized the weight distribution of the 6th motor on the robot, which is actually on top of the lift. It controls the arm rotation here. And we used it as a counterweight for the arm so that the motor would have to draw less current when flipping the arm from one side to the other. So as you can see, all of the heavy components on the robot were very intentionally placed to maximize its performance. Now I'll turn it over to Sherwin for the software.
Yeah, so over on our software, actually this year we had a lot of sensor optimizations. For example, when you're picking up off a cone stack, you don't know how tall the cone stack is. But instead of having to pre-enter that information, we actually use our lift as sort of a sensorless homing system where we press our lift down into a cone stack to detect how tall it is. We also have beam break sensors in our cone pickup area so we can auto pick up once a cone's detected. But I think the biggest thing that we implemented starting this year was a bunch of robot optimizations with our finite state machine. So over on all our slides, you should see a flowchart where we have our robot state, which is essentially a finite list of states that a robot can be in, and a bunch of well-defined connections between those states. And this allows us to predictably control our robot's mechanisms, switching from one state to the other without any weird edge cases as much, and also optimizing the paths between them. Also, another thing we do with our state is control optimizations. For example, our robot's arm starts in the upright position, And once we want to intake a cone, the first thing we do is first bring our arm down to prepare the pickup. And then after that, we actually pick up the cone. And this two-step process could be delegated to 2 separate buttons, but we actually have one button that does a different thing depending on the current state of the robot. And the good thing about this is, A, you save less, you use less buttons on your controllers. We actually don't, I think we have the least buttons that we have in all our past seasons on our controller. And also the other thing is that psychologically, you only associate one button with getting to the pick up a cone state, which is pretty useful for reaction time. And then moving on from that, another thing we did this season was use a slow-mo camera on our phones actually to optimize our pickup process. Because when you look at the robot in slow motion, you can see where you're losing all your times in delays. And we use that information to parallelize our processes. And even if you just save like 500 milliseconds or something in your transfer, that's a really small amount of time, but throughout autonomous, that adds up. And we were able to shave off a few seconds and increase the amount of cones that we can score with the time we have in auto up to a 1+5 autonomous once it's fully optimized. Now moving on to our vision pipeline. During autonomous, we auto-align to the pole we're scoring on using a camera that's built into our grabber that actually looks through the cone that we're currently holding. And the way this algorithm works is in a few steps. First, we use a flood fill algorithm to take all the yellow pixels in the image and group them into individual poles. And then once they're grouped, we can individually score each of them using a heuristic to figure out which one is the most likely to be the one that's centered and that we're going for, and also not just a random yellow piece on some robot. And then once we've selected a pole, we can calculate the trajectory for it and go for that pole. And we've actually had a few optimizations in this process, because in past years, we have had color detection algorithms before. But this year, our algorithm that detects all the yellow pixels is the most advanced we've ever made it, where typically what we used to do was have a set threshold for how yellow something should be to be considered yellow. But this year, we actually don't have a set threshold at all. We use a statistical algorithm to figure out the most significant yellow pixel, just to find the yellowest thing, which makes it independent of lighting condition. We also test the colors in the HSV color space, so we can test the hue to be in the yellow region, regardless of saturation or value, which helps with being independent of any lighting conditions, which made us more reliable. Also, another thing is instead of averaging all the yellow pixels in the image to find the center pole to go for, we individually group the poles and target them individually. Because if you were to just average all the pixels, one pole off to the side could shift your average over. And so that wouldn't be necessarily optimal heuristic to use. So instead, using flood fill allows us to look at all the poles individually and pick the best one and then go for that. And yeah, our vision algorithm has been pretty successful this season, and we've been able to improve our auto reliability, and it worked pretty well. And I think, yeah, those were some of the main innovations we've had this season, and we'd love to talk about any more and any questions that you might have.
Yeah, we got a few questions coming in already, everybody. So starting out from FTC Robo Players, they want to know more about your side plates and what they're made of.
Yeah, so our side plates, we use a laser cutter. So these side plates are made out of Delrin. And Delrin is a very strong material, but it can be pretty flexible on plates of this size. And so we use a couple different strategies to make them as rigid as possible. So the first is what we call the sandwich technique. So we basically put 2 Delrin plates next to each other with a whole bunch of standoffs in between. And this basically has the effect of redirecting the force from one that is bending the plate to one that is compressing and extending the plate. And this is a direction in which Delrin is very strong in, and it's basically allows us to have, for example, our chassis assembly has a plate on each side, and this allows us to make everything really rigid. Another strategy we use to make them very rigid is triangles. Triangles are very strong structures, so you can see our robot is actually kind of one big triangle with the shape of the plate, and then we also have some other internal triangles that brace it in the other axes to use this material.
And also, so Delrin is a plastic, and the reason we use it is that it can be laser cut, like Nico said, which is just a lot easier and faster process than machining something. But yeah, we do have to take more care when using it because it is not as rigid and it's easier to bend. So, yeah.
Next question coming in from John Cannon. Wants to see a little bit more about the mechanism for using one actuator to control 3 different mechanisms. Could you elaborate a little bit more on that?
Yeah, so this is our intake claw up here. let's see. Yeah, you can see that. So our intake claw just opens up and closes like that. So our capstone actually has a special design that allows it to basically hook into the top of this claw. So when we grab a cone with the capstone on top of it, the claw itself is grabbing onto the cone just like normal, but then there's a little hook that allows the capstone to basically attach to the claw itself, so that when we open the claw just a little bit, the claw will let go of the cone and the cone will slip through and score onto a pole. But then the hook on the beacon will still be hooked onto our claw mechanism. And so this allows us to switch to a different pole and then open the claw all the way, and that will release our beacon. And then the third system is, well, it involves more than just that one actuator, but basically we can come down onto a cone like this and then drive backwards. And that allows us to basically tip forward a cone.
All right, we got a couple more questions. Let's go a little bit quicker on them. But from Screen 404 asked, what trade-offs did you have to make in order to use? I'm going to read this phonetically, so hopefully this will be all right. What trade-offs did you have to make in order to use so few actuators?
So it was actually very nice because there's lots less code that you have to do to control all of the systems. And everything is just much easier to control. And then, yeah, there's also, like, for example, on the scissor lift in the back here, we have a whole wiring guide that brings the wires all the way up to the lift system. And so because we have fewer actuators, there's less cables that we have to route up as well. So, yeah.
All right, and last question coming in from Seedlake Sinton. Was there any feedback given to the drivers from your vision pull detection algorithm, or was this only used for autonomous?
We initially did try to add a button that would automatically align the robot to the pole during driver control, but we actually found that the driver, which is Sherwin here, could align to it much faster than the vision could during teleop. So we removed that feature and we align only manually.
Yeah, I think the poles being compliant and you just being able to push the cone into them meant that it's not as important for the driver stage when you're just driving up to the cone as auto.
Yeah, and we also have a wrist mechanism that tilts the cone towards the pole. So this eliminates one axis of alignment, and so it's much easier for both autonomous and the drivers to align to a pole.
All right, 14496 Roboctopi, thank you so much for telling us more about your team, and congratulations on a fantastic season. And good luck in Center Stage coming up very soon. Thanks a lot, guys.
Thank you so much.
Thanks for having us.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in FIRST scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first.
Hi, we're Team 7172 Technical Difficulties, friends and family team from Plano, Texas. My name is Akshay.
My name's Hebe.
So to start off, I'd like to talk about the robot design. And more specifically, I'd like to talk about our extending drivetrain. So to start off with, the reason we implemented the extending drivetrain in the first place was it would allow us to reach both cone stacks in the autonomous portion, leading to a potential 1+10. Though we never were able to tune the autonomous to get a 1+10, um, there were other benefits to using the extending drivetrain. So one of the main benefits is for defense. So without the extended drivetrain, if a robot were to park themselves in front of us, both of our arms would not be able to go down to intake. And one of the ways that our extending drivetrain solves this problem is that while we're extended, we're still able to score on most, if not all, of the same poles. But we can also reach around the opponent robot that is blocking us. And so the way it works is that each side of the robot is drives in opposite directions, and it's kind of a differential in the way that with a normal drivetrain, if you try and send your two sides of your robot into different directions, your robot will probably slip, your wheels will slip, or your robot will break. But if you were crazy like us and connected the two sides of your robot with Masumi slides, your robot would instead extend. And that's kind of how ours works. So one of the mindsets that we used here was if you take two two motors that are driving the same mechanism, or in this case it's four motors and it's our drivetrain, and you kind of experiment with what you can do with the different ways your motors can turn and using the difference between them. That's what gets you a differential. For example, if you had two motors on your elevator and you had them run the same direction, and made it extend, or run in opposite directions and have like an arm flip on top of your elevator, you would have a differential. And that's exactly what Infinite Turtles, I believe, did in Freight Frenzy with their elevator. So, but one of the things that is an issue with differentials is simply the programming complexity. And so one of the ways I can explain that is, so for us, when we were trying to tune our 1+10, it was the equivalent of trying to make two robots score on the same pole without interference during the autonomous portion, um, which is very difficult, and you generally don't see two teams scoring on the same safe pole in their own alliance. Um, so if you were wondering about how rigid the Masumi slides and the whole extension of our robot is, I'd say there's about an 8mm drop when our robot is fully extended, which is 5 feet. So there's an 8mm drop between the middle of the slides and the ends of the robot, which, as you can see, is definitely rigid enough for us to be able to score. So I'd say if you wanted to use extending drivetrain, Masumi slides would be the way to go. So moving on, the next part I wanted to talk about is our arm motion. So on each arm, we have at the base we have our turret. The turret is a 5.2 to 1 Go Build a motor, driving a Go Build a worm gearbox. It's the super duty or heavy duty worm gearbox that runs about a 28 to 1 ratio, I believe, the worm gear. And this has been really consistent for us. We never had to iterate it much. Just if for anyone who is planning to use this, do be aware that you do need to tune the distance, the center to center distance between your two worm gears. On top of that, we have our first pivot. Our first pivot is Go Build a 19.2 to 1 motor going into a 10 to 1 industrial CNC worm gearbox. And the reason we chose this gearbox is because when you have a 4-foot long arm, or just a really long arm, that's a lot of leverage, which means you get combined with all the moving parts on the arm, you get a lot of slack in your arm. So we wanted to try and minimize it as much as possible, and especially on the base. Um, to help both the motor lift the arm and to um, make the slack in the arm a little bit more bearable, we use counterspringing. Specifically, we put a 40-pound torsion spring on each side of the arm, and you can kind of see it in the stream of the robot. Um, but as the arm goes down, the spring is engaged more and more, causing the spring to push back against the arm more and more as the leverage that gravity has on the arm increases, the spring pushes back with a proportional force. One of the issues we had with this first pivot is earlier in the season, we used a Delrin coupler. And as many people know, plastic against metal in general is not a smart idea. So at one of our competitions, the arms clashed and that stripped. So just a little bit of learning from our part. Um, so moving on, this in one of our older iterations of the arms, we had um, a second pivot, and basically it was rather than a linear extension on each arm, you had a second joint. So as you can kind of see in the video, um, it was another point of motion, and it was driven by 2 axon servos. And the issue with this was when you already have your 4-foot long arm, as I mentioned earlier, the slack adds up. And specifically with this design, since the axon servos were chained to each other, or there was an axle going between them, and then they were chained to the arm again, uh, just the amount of slack that builded up there was just intolerable, or just not very good to work with, especially in the autonomous portion where you want your arm to be really accurate height wise, so that you can pick up cones off the cone stack efficiently and without dropping cones or grabbing them at the wrong point. So, which is why we transitioned to a linear arm, or arm with linear extension on it. The way our linear extension works is it's two Masumi slides, 2-stage Masumi slides stacked on top of each other. Each one is driven by a GoBuilda 5-turn super speed servo, along with and then gear rack, and a gear and gear rack. And then because we're able to use the GoBuilda super speed servos with the servo power module, we had enough torque and we were able to extend our arm in about 0.8 seconds, if not less. Then we have our third pivot. Our third pivot is just pretty simple, just an axon servo, which allows our arm to be level with the ground or slightly angled, no matter which cone or which pole we're scoring our cone on. Then we have our wrist. This is what allows our arm to flip over this is when our arm flips over in the autonomous portion. When the wrist flips over, the guide is engaged, and then we're able to use the guide to score on the pole, rather than having to, and we're able to flip over rather than having to turn the arm all the way around. Last but definitely not least, we have our grabber, which is definitely the most iterated part of our robot. We started with gear and a different claw design that had too little torque, so we went to a double over the center linkage, which had a lot of torque but not enough range. Which for us, when we have one arm waiting at the substation and the other arm, as soon as the other arm lets go of the cone, you want to be able to grab that cone. So we want to be waiting at the substation, but we can't be inside the substation, or else our human player can't put a cone for the other arm. So we looked at the Looney Claw, and we used the portion of the claw which uses the double herringbone gear, and that which reduced the backlash, and rather than increase the torque, it reduced the backlash, which helped with the issues we had with the first geared version. And then we used a overcharged or revamped style claw at the end with 4 surgical tubings. And what all of this allowed us to do is, with the end grabber, we were able to grip the cone at any height. We had a wide range in which the cone could be placed, and we were able to stay outside the substation without having to move any other joints besides the grabber. That is all I have for the robot section, or the hardware section.
Again, my name's Hebe, and I will be talking about the programming aspect of the robot. Sorry, my light just cut out for a second. First, we start with the arm code. So to control the two arms on the robots, the code takes 3 parameters: the desired turret angle, pivot 1 angle, and extension length. Using these parameters and an array of constants such as gear ratio and arm lengths, the code performs inverse kinematic calculation to determine the correct servo and motor position so the arm reaches the position we want. This method also allows us to keep the third pivot at the constant angle relative to the ground, so that the cone always stays upright. Because the robot doesn't know where the arms start at the beginning of autonomous and teleop, we use the absolute linear potentiometers on the turret and first pivot to know the starting position of the arm. Unfortunately, as shown in the graph, which comes up in a second, the control and expansion hub doesn't read potentiometer voltages linearly. To combat this, we use a calibration process for the turret and first pivot that involves sweeping the motor's range and recording the motor encoder's values and the potentiometer voltages at various points to create a lookup table. This lookup table is referenced at the beginning of every program to establish the arm's GWP positions. Since the arm on the robot can reach up to 4 feet, the possibility for collisions with poles is extremely high. So we use motion profiling to control the arm's movement so that no collisions can occur. First, the arm retracts the extension and angles the first pivot upward toward the robot. Then the turret turns to its target angle. When turret finishes, the first pivot and the extension move to their targets. At the end of each arm, we have a Husky Lens camera. The Husky Lens is an AI-enabled camera that is capable of tag, object, and color recognition. It features onboard computing and is a lightweight solution to computer vision. We use the Husky Lens to follow the yellow contour of the pole while scoring in Auton and teleop. As Husky Lens has never been used in FTC before, we developed a customized I2C driver that allows the Husky Lens to interface with the rev, control, and expansion hubs through the I2C device ports. As part of our teleop optimization, we use automated presets to allow the drivers to quickly score on different poles with the press of a button. In the teleop, we have modes for different locations that we score from on the field. The first is called Gold mode, which can be seen here. In case we encounter a robot playing defense that parks in front of us, we also have Silver mode, which utilizes the extended drivetrain. Both modes have their own scoring presets. And that will be the end for programming. If you guys have any questions, feel free to ask.
Yeah, we do have a couple of questions in chat that have come through on here. The first one's going to be from Screen 404. Thanks a lot for all the great questions, everybody. Screen 404 asking, was having two arms difficult to control and coordinate during the competition? So can you talk to us a little bit more about what it was like in a match to actually try to control these crazy arms that you have on your robot?
Aki, do you want to go first, or?
Sure. So, Hebe, you can talk about the software side of this, but so from a driver perspective, there's on the gamepad they have their presets for low, mid, and high on the AX and Y buttons. Maybe not those exact ones, but for example, and then using various shift buttons, you can change it to high 1, high 2, mid 1, mid 2, and basically with a combination of these 6 buttons and the software presets, they're able to move the arm to wherever in the field, and each arm is controlled by one driver. And then the arms also have software limitations and automations. So go ahead, Hebe.
So for the arm code, we have limitations for the arms, so to avoid the two drivers clashing it together during matches, and we also have limitations. So usually, only one arm is allowed to pick up a cone or anything, unless it's during the end game when the driver and the team shipping, like the cone and the team shipping elements, are both being picked up, which avoids us getting penalties. Since if one is picking up, the other one cannot pick up a cone. And that's pretty much the hardest coordination aspect of the two arms.
Yeah, last question we're going to take for 7172, everybody, is going to be from John Cannon, asking about what would you have done if someone else damaged the weaker link between your two halves? So if you would have taken damage while your robot was extended out, how would that actually impact your robot in a match?
So this never happened, so this is probably a purely hypothetical answer. So I assume this is sometime before endgame. So I guess the drivers would have to keep the drivetrain extended. And although this would make moving across the field difficult, which would mean we probably wouldn't be able to park as easily in endgame, we would still be able to score from that one spot, or what we call our gold position, where we just stay in the one spot and score. Um, if if it were damaged to the point where we could retract but not extend again, I wouldn't think it would be too much of an issue because I guess realistically, we've used the extension mainly to just get cones out of our robot that have fallen in to avoid incurring penalties.
Oh, thank you so much to 7172 Technical Difficulties. One of the coolest robots I think I have ever seen in my entire FIRST history. So thank you very much. Good luck in the Center Stage season coming up in a little bit. And if you're watching live, we have one more team coming up, 16458. TechnoWizards will be up in just a few minutes. Thanks a lot, Technical Difficulties.
Thank you for hosting us.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. At Kettering University, over 30% of the student population was in high school robotics. These same students have received a portion of over $7 million in FIRST scholarship. Scholarship applications will open in September. Get ready to go pro and get more information at kettering.edu/first. Sweet. Oh, I just put the wrong team up. 1 second.
Hello everyone, I'm Parker from 16458, the TechnoWizards, and I'm on the mechanical team.
And I'm Justin, and I'm from the programming team.
So in today's presentation, there's two main topics that we're planning on covering, and the first one being the importance of a proper brainstorming process, and secondly followed by improving autonomous reliability through robot design, and as well as kind of how our robot this season was optimized through robot design for autonomous performance. So I will get into that later. So first of all, I think Justin can talk about this.
Yeah, so first off, I'm just going to give a little brief introduction about our team. We're the TechnoWizards, team 16458 in San Antonio, Texas. We are an 11-member community team. We actually just got 3 new members this year. We've had 9 years in FIRST and 5 years in FTC. So a couple things that we achieved this year is that we were world champ semifinalists in the Ochoa division. We also came out as First Inspire Award winners at the Central Texas Championships. We won First Design Award at the Texas State Championships, and also we had the first highest OPR in Texas in qualifiers.
Okay, so next I will actually start beginning our presentation, and I'm going to talk a little about the importance of brainstorming, actually having a good brainstorming initial design process when you start a season. So before I get into our brainstorming design process for initial design, I'm going to talk a little about the importances about what we learned this past season on kind of the importance of having a good brainstorming process. And there's 2 main points I want to cover. And the main one is this eliminates need for later in the season for you need to rebuild your robot. So a lot of teams aren't capable of rebuilding a robot later in the season due to time constraints. And the main benefit of actually having a good brainstorming process at the start of the season is you're able to eliminate inefficiencies in your design. And this allows you to keep one single design that's good, efficient, and reliable throughout the entire season. And this can save time and allow you to iterate on specific parts of your robot that you want to improve later on the season. And it's also better if you just have a good initial design at the start because it allows you to perform well in competitions, obviously. Second of all, like I kind of already mentioned, it also allows you to iterate on specific parts of your robot that you want to change and modify and improve on. If you have a poorly initially designed robot, this means that your entire basis of design is kind of messed up, and improving just one portion, one aspect of your robot may not be beneficial as much as completely redesigning, which I mentioned may take too long. So it's better if you have a good initial design process to leave you time later in the season to actually be able to modify specific parts. So now going into the initial design process that we personally used last season, I have listed 4 main steps, but it's not really a step-by-step process. It's kind of a flowing motion that we go through. And first and foremost, a little bit of common sense, like duh, but you need to read the game rules. You need to analyze them very intensively because you need to be able to know what your design constraints are. You can't just design anything. You need to be able to know what is legal, what is illegal when you're designing a robot. So design constraints are very important. The second point in our initial design process is really the most important one and the one that we focused on the most last season and we benefited most and allowed us to succeed the most was actually assigning values, which is completely new to us. And when I say assigning values, I'm talking about assigning importances and kind of creating a hierarchy of specific aspects of the game that you find most important. So just kind of an example of that last season, one thing that we really wanted to focus on and what shows a lot in our robot design was autonomous performance. So we valued autonomous performance extremely high because of how the fact that cones were counted twice and that parking was the same amount of points as completing a circuit. So we saw optimizing autonomous aspect of our robot to be extremely important. So when we designed a robot through initial design process, we wanted a robot that hit on every single aspect of autonomous in a reliable and efficient manner. After assigning these specific values, we go into team brainstorming. Oh my God, sorry. Okay, there you go. Team brainstorming. And in team brainstorming, it's just as it sounds, brainstorming as a team. Personally, we like using a whiteboard so we can display ideas out in an open manner to allow each of our team members to contribute ideas to each other. But we also find using resources such as GM0, which is really great resources, which is written by FTC teams, and it has countless documents and countless components that past teams have used on their robots, and a great introduction to specific aspects. You will learn more about designing a specific part if you want to design so. Also helps with coming up with ideas. We also found looking at past seasons and other team designs also really helped us design a robot. A lot of robot has been inspired by teams of past seasons and looking at what they did and what helped them succeed and trying to apply those same concepts in our team this year. And a lot of that contributed to our robot design and overall our success. We really recommend teams looking at that. And then finally, and really important, is design confirmation, in which those designs that you came up with team brainstorming, you actually try simulating these designs, you CAD them, and you do design visualization to make sure these designs are actually reasonable, you can actually accomplish them, and they're within a time frame that would be reasonable for your team to actually build in time. So a lot of stuff that you do in team brainstorming, we like to do design confirmation, make sure that our designs that we come with are actually reasonable. And like mentioned, we do that a lot through CAD and visualization. So next, I'm going to talk a little bit about what we came up with through our design and brainstorming process this season when we designed a robot. And there were 3 main topics, like I mentioned in stage 2 of the design process, initial design brainstorming process, assigning values. These were the main values that we assigned to a robot's design this season. And these were optimizing design performance and reliability. We also wanted to very highly rank junction ownership and also reduce driver workload. We found that this season, because there are so many different spots where you can deliver, and there's so many poles, there's so many junctions, you can deliver on the ground, you can deliver on ground junctions, you can deliver on different heights of poles. We found that it would be very beneficial to reduce driver workload as much as possible, and that kind of showed in our robot design, which I can go over a bit later. And then, so optimizing optimizing autonomous performance. Main tips that we found when you're designing a robot in order to optimize design performance. Sorry, I'm moving on to the second topic of the presentation now. So the main things that we figured out from last season that allowed us to actually have a very well-designed robot for autonomous performance was prioritizing and eliminating variables as much as possible. And when I say variables during autonomous, I'm talking mostly about localization errors. We found looking at past seasons and what caused a lot of teams to have unreliable autonomous was from poor localization, whether it's be from biodometry tuning or other forms of localization. Getting off on accuracy from driving caused a lot of unreliability during a lot of teams' autonomouses. So we find prioritizing, eliminating this kind of variable and what other variables such as climbing for other robots to be as helpful, to be one of the most helpful things to help increase autonomous reliability. Secondly, what we try to do and what other teams should try to do is implement fail-safes. And a lot of fail-safes we implemented this season was through sensors. And one example of that is kind of for intake. Our intake, we have a basic cloud like a lot of other teams have. And within our intake, we have a distance sensor. And during autonomous, one of the main things that we do is looking and seeing if we detect a cone. If we don't detect a cone within a certain amount of time, then our robot is able to assume that maybe the stack got knocked over, maybe our intake system stopped working and didn't extend all the way. And one of those specific needs doesn't get met, then we know to stop running autonomous, stop delivering, and actually just go and park in order to enter autonomous early. And implementing a lot of those fail-safes can help maintain a high autonomous reliability and help maintain scoring even with one part of your autonomous failing. And lastly, one thing that a lot of teams should focus on that we feel is optimizing it for a design that increases reliability instead of trying to create a designed robot that does not focus on actual potential during autonomous. So one thing that last season a lot of teams scouted for, it's much better, in our opinion, to scout and find a team that had an autonomous that could do a 1+3 very reliably 100% of the time versus a robot that could do, let's say, 1+5 but only work 50% of the time. Because although they have a higher scoring potential, their reliability is not at a point where we'd be comfortable picking them. And having a robot that's very reliable at a specific task, especially during autonomous, is very valuable, not only to optimize your autonomous performance, but also in scouting and alliance selection. So next, I'm going to start the next portion of our presentation where we kind of talk a little bit about debriefing our robot and how we kind of specifically try to accomplish some of the tasks that I talked about earlier and optimizing design performance. So the main thing that we focused on this season, or the main innovation that we kind of had this season that we focused on, was having 2 turrets. And by 2 turrets, I basically mean having a turret on our intake system, but also having a turret on our delivery system. And what this allowed us to do is our robots remain stationary while cycling and autonomous. And if we swap to our camera, I can kind of showcase how the 2 turrets look visually. This is our intake system, and during autonomous, once we drive to the cone stack, which would be maybe right here, our intake would turn 90 degrees, such as, and then our delivery turret would be able to turn 45. And this will allow us to do is a robot doesn't need to move it all while cycling. Our intake can extend out, and our delivery can extend out, and our robot doesn't need to rotate at all. And all it has to do is sit in one position, and this allows us to reduce a lot of localization as a lot of our teams may have had in the previous seasons. This also reduces chances of collision with other robots because we're trying to stay on our side of the field away from other teams. So that's the main point of our double turret system, and that showed a lot in our autonomous accuracy this season. So nextly, the next thing that we had and we brainstormed that we wanted to use to increase autonomous reliability was through having both an intake and delivery extension. And this is much like our reason for having our double turret system. Having both an intake and delivery extension allowed a robot to remain stationary. So I guess I can showcase that again. Our intake extension goes out such as, and this allows us to grab cones from the cone stack. We have a virtual 4-bar with a claw that's just able to grab the cones at different heights and deposit it back in our transfer system. And using the intake extension prevents our need from the need of the robot to move horizontally or different motions. And we also, of course, have our delivery extension, which allows us to deliver to the pole at an angle and also at multiple heights. Because in some matches, you may want to deliver to the medium junction or to a dodge opponent. So that's how we used 2 extensions to improve autonomous accuracy. The last and final most important part that we found that allowed us to improve autonomous accuracy this season was having a pole liner implemented. And I know a lot of other teams have this, but the way we did it, I guess, was a little unique, which I can showcase. One thing we wanted to focus on with our pole liner was to have it be able to deploy without any servos. It's a free deploying pole liner. And the main reason we had that was to reduce weight on our delivery extension so we can have a faster extension time, but also reduces complexity so there's less actual servos and actuations that's happening. So the way it works is we just have it auto extend out. We have a bungee to pull it down so it's always extending to the same position. And what this basically allows us to do is just vector the pole within our delivery claw so we can deliver on the pole in the same position every single time. And this really just allows us to eliminate inaccuracies in fields so we don't have to worry about maybe if this one field that we're playing on has a pole tilted this way and this other field has a pole tilted this way. We can eliminate those field inaccuracies with our pole liner. So that was the main point for that. And that pretty much concludes our presentation. If there are any questions, we would gladly be able to answer them. If not, thank you for having us on.
A couple questions that we'll be asking from the chat coming in. First off, from the Bakari, asking, how did you wire your double turret design?
So with our wiring, it was a little complicated. We did, if we swap to the camera, we did have problems at the beginning of the season with, because our extension's so long, on our intake system, we needed wires to run all the way from our expansion hubs all the way out to our cloud here because it flows all the way through. So we had initially just soldered wires together, which wasn't great because we had to compact this all in one location. And when the wires came together, we had to actually fold them in at the spots where we soldered the wires together. This could cause the connections to loosen. So we basically ended up just having to make our own custom cables, and we soldered our own custom cables. So everything running from our control hubs, our expansion hub runs all the way through, and it's just one cable that we have running all the way through for each one. And specifically, you asked how we wire the double turret system. Within our robot, we have a bungee, and at the back, we kind of have a little bit of a mini turret where it's kind of hard to showcase, but I can explain a little bit. We have a mini turret where all of our connections come out of, and this allows all our wires to free spin at the back of the robot so they don't become crimped or they don't just get crunched up. So when our intake spins, there's a rotation movement back here where all the wires can rotate, and they're all held together through a bungee. That's kind of how we do it.
Chat will give a couple more minutes from questions if anybody else has any. We do have one coming in from James Liu asking, can you talk a little bit more about the your transfer system, asking specifically how did you transfer the cones between the two slide systems?
Yeah, so with our transfer system, it's pretty simple. We have our basic intake claw. It's on a virtual 4-bar. We have our distance sensor, which allows us to automatically detect cones. And when this happens, the whole system is automated and we deliver. And right here, we have a funnel system. And with the funnel, a cone can be dropped in many different positions and they all kind of funnel back in the same spot. And it's just possible for reliability issues that we had earlier on in the season. And when they're all funneled in one spot, we have our second virtual 4-bar, which can come down and grab cones, and we just deliver. So the 4-bar will just come down and grab it. Our 4-bar is kind of broken right now, so I can't show that.
It's been a long season. No worries on that at all. TechnoWizard, thank you so much for telling us more about your team, your robot. Congratulations on a great season. We look forward to seeing you in Center Stage as well. Thanks a lot.
Thank you so much.
Thank you.
And that's going to wrap it up, everybody. Thank you so much for watching our conference here today. You'll be able to find archives on this at youtube.com/firstupdatesnow. It should be live on demand right now. So thank you, everybody, and have a great evening.